The detection began not with a visual confirmation, but with a mathematical discrepancy. In the high, thin air of the Chilean Andes, where the Veracruz Observatory scans the southern sky, automated algorithms sift through millions of transient points of light every night. Most of these are familiar ghosts, main belt asteroids drifting lazily between Mars and Jupiter, or distinct comets falling inward from the Oort Cloud on long looping tethers. They obey the gravitational laws of the sun, moving at predictable speeds, tracing ellipses that, however stretched, eventually close back upon themselves. But on a Tuesday in late October, the code flagged a solitary point of light that refused to conform. It was moving too fast when astronomers turned their attention to the coordinates. They expected to find a glitch, satellite, reflection, or a sensor error. Instead, they found a rock. It was faint, barely a smudge against the velvet backdrop of the constellation Cetus, but its motion was undeniable and alarming. Every object born of our solar system orbits the sun. They are captives of our star's mass. This object, however, possessed an excess velocity that defied capture. It was traveling at nearly 90 kilometers per second relative to the sun, a speed that liberated it from the gravitational mandate of our local space. It was not falling around the sun, it was falling through the system. It had plunged from the interstellar north, pierced the plane of the planets at a steep, impossible angle, and was already beginning its exit before we even realized it was there. We named it Atlas. The designation 3I implies a sterile sequence, the third interstellar visitor catalogued by human history, but the name suggests a burden. In mythology, Atlas held up the celestial sphere. Here, the object seemed to carry the weight of the galaxy's vast, unmapped history upon its dark surface. Unlike the dusty, craggy asteroids we have sampled, Atlas did not reflect the familiar spectrum of silicate and iron we associate with the inner solar system, as the great telescopes of the world swung to track its retreating form. The light curves revealed a surface that had been weathered not by the solar wind, but by the harsh, unfiltered radiation of deep space. The spectroscopic analysis painted a picture of something incredibly old. The surface was a deep, matte red color characteristic of tholins, complex organic compounds formed when methane and ethane are bombarded by high-energy cosmic rays over hundreds of millions of years. This reddening is a callus, a scar tissue built up over eons of drifting in the void. It told us that Atlas had not seen the warmth of a star for an eternity. It had been tumbling through the obsidian silence between systems, a lonely traveler, suspended in the freezing dark, long before human beings walked upright, perhaps long before the dinosaurs reigned. Its last encounter with warmth was likely the fiery death of its parent star, an event that ejected it violently into the galactic current. As Atlas approached its perihelion, its closest point to the sun, we waited for it to awaken. When from the fringes of our own system draw near the sun, the heat sublimates their ESOS, creating a brilliant coma and a trailing tail of gas and dust. We expected Atlas to exhale. We anticipated a plume of water vapor or carbon monoxide that would allow us to taste its chemistry directly. But Atlas remained stubbornly silent. It passed within a fraction of the distance between Earth and the sun. Baked by solar radiation intensities it had not experienced in eons, yet it released no gas. There was no coma, no tail. It was a dead stone, or perhaps something so dense and metallic that the heat simply washed over it, absorbed into a cold heart that refused to melt. This lack of outgassing forced a recalibration of our theories. If it wasn't a comet, and it was moving too fast to be a normal asteroid, what was it? The light curve data, the way the object's brightness dimmed and flared as it moved, revealed that Atlas was not spherical. It was elongated, a splinter, a Flannery crust or a shard of a shattered moon, tumbling end over end in a chaotic, non-principal axis rotation. It did not spin smoothly like a top, it tumbled like a thrown hammer. This violent rotation suggested a traumatic origin. It hinted that Atlas was born from a cataclysmo-planetary collision, or a gravitational shredding event in a star system, light years away. It was debris from a wreck that happened in the deep past. Flinging shrapnel across the galaxy, the silence of its passage was perhaps the most haunting aspect of the encounter. Here was an object from an alien world, a physical piece of a star system we will likely never see, passing within the reach of our sensors. Yet, it offered no greeting. It was indifferent to the planets it passed. The immense gravity of Jupiter, usually the bully of the solar system capable of bending the paths of passing comets, barely nudged Atlas's trajectory. The object was moving with such kinetic purpose that the combined mass of our planets was little more than a background fluctuation to it. It treated the solar system not as a home, or even a destination, but merely as a patch of friction to be overcome. As it crossed the orbit of Mars. Heading outward, the geometry of the viewing angle gave us one final, clear look. In those fleeting nights, we realized the scale of the object. It was smaller than the cities that built the telescopes watching it, perhaps only a few hundred meters across. Yet it represented a statistical reality that is difficult to comprehend. For every object like Atlas that we detect, there are trillions that pass unnoticed. The galaxy is not empty. It is thick with these wanderers. We exist in a blizzard of ejected stones, a cosmic rain that has been falling since the first generation of stars ignited. Atlas was simply the one snowflake that caught the light. The data streaming down from the observatories became a global obsession, yet the interpretation remained quiet, rigorous, and slow. There were no press conferences announcing little green men, only the somber realization of the scale of the universe. To look at Atlas was to look at a tombstone of a forgotten world. The isotopic ratios hinted at a metal-rich composition, implying it came from the core of a differentiated planeta world that once had a molten center, a mantle, perhaps even a magnetic field. That world is gone, ground to dust or swallowed by its star, but this fragment survived. Carrying the encoded memory of its geology across the gulf of the Milky Way, we watched it dim. The speed that brought it to us was now tearing it away. Every second, it put another 90 kilometers between itself and the sun. The narrative of its visit was short, lasting only a few weeks of optimal viewing, but the implications rewrote our map of the local neighborhood. We had long believed that the Oort Cloud was the limit of our domain, a shell of icy debris marking the end of the sun's influence. But Atlas proved that the border is porous. The solar system is a sieve. We are constantly exchanging matter with the rest of the galaxy, trading dust and rocks in a slow, invisible metabolism that links our star to its neighbors in the spiral arm. This realization brought with it a subtle shift in our psychological orientation. We are not an island. We are a house with open windows, and the breeze blowing through carries the dust of other places. Atlas was a tangible piece of that breeze. As the object faded from the visible spectrum, becoming a ghost, traceable only by the most sensitive infrared instruments, the scientific community settled into the long work of analysis. The excitement of the chase gave way to the quietude of calculation. We began to trace its path backward, reversing the clockwork of the orbits to see where it had been. The trajectory did not point back to any of the nearby stars. It pointed to avoid a gap in the constellations where no bright star currently sits. This meant that Atlas had been traveling for a timescale that dwarfs human history. It had likely been adrift for millions of years, crossing the grand spiral arms of the galaxy, dodging the gravitational wells of other stars, surviving the erosion of interstellar dust, only to accidentally thread the needle of our solar system. The odds of this specific intersection were astronomical, a winning lottery ticket drawn by a dead rock. It forced us to confront the sheer density of the stuff in the void. If we saw this one, how many millions passed by just outside the range of our vision? How many have crashed into the sun over the last 4 billion years? Their alien isotopes vaporized and blended into our star's plasma. We are accustomed to the idea that we are made of stardust, that the atoms in our bodies were forged in the hearts of dying stars. But Atlas reminded us that the delivery mechanism for that material is often violent, random, and ongoing. It was a messenger from the era of planet formation, a time capsule preserved by the cold. As the distance grew, the signal-to-noise ratio dropped, and Atlas began to merge back into the static of the background universe. It was returning to the dark, returning to the anonymity of the interstellar medium, but it had left a mark. It had scratched the lens of our perception. We could no longer look at the black space between the planets and see it as empty. We now knew it was a highway, and traffic was moving in both directions. The universe, as we perceive it today, is rarely discovered through the eyepiece of a telescope held by a shivering astronomer on a lonely mountain peak. That romantic image belongs to a previous century, a time when the cosmos was small enough to be captured by the human eye. Today, the discovery of the unknown begins in silence. Within the humming, climate-controlled aisles of server farms where algorithms tirelessly sift through the digital memory of the sky, modern astronomy has become a form of archaeology. We are digging through layers of light that have already hit the sensors, searching for patterns that the machines might have missed on their first pass. The sky is no longer just a view. It is a database, vast and deepening every night, waiting for us to ask the right questions. It was in this quiet, archival dark that the anomaly first appeared. It did not announce itself with a flash or a roar, but as a subtle discord in the coded set of coordinates that refused to align with the expected geometry of our solar system. The automated surveys, designed to track the thousands of rocks tumbling between Mars and Jupiter, classify objects based on familiarity. They look for ellipses. They look for closed loops. They assume, fundamentally, that everything they see belongs to the sun. When the object eventually designated as 3I Atlas was first flagged, the software paused, not because of what the object was, but because of where it wasn't going. It was a trace of light that broke the rules of local gravity. To understand why this faint scratch on the darkness mattered, one must first understand the invisible architecture that governs our celestial neighborhood. For billions of years, the solar system has operated like a grand, complex clock mechanism. We have the planets, the heavy gears, turning in predictable, circular paths. Then we have the comets, the wilder, erratic pendulums of our system. These comets come from two specific reservoirs, two distinct homes that we have mapped with confident precision. The first home is the Kuiper Belt, a scattered ring of icy debris just beyond Neptune. The comets born here are the short-period travelers. They visit us frequently, their orbits taking perhaps a few decades or a century to complete. They are the familiar neighbors, predictable and tethered. The second home is the Oort Cloud, a vast, theoretical sphere of icy bodies that surrounds our solar system like a shell, extending almost a light-year into the void. Comets from this distant, frozen hinterland are the long-period visitors. They fall inward on steep, elongated paths, taking thousands of years to swing around the sun, before retreating back into the shadows. But whether they come from the near ring or the distant shell, they all share one defining characteristic. They are captive. Their orbits, no matter how stretched or eccentric, are always closed. They are bound to the sun by an invisible chain of gravity that they cannot break. They fall in, they swing around, and they return. This is the standard model of cometary behavior, a set of laws that has held firm since Newton first scribbled his equations on parchment. It is a comforting model because it implies a closed room. It suggests that while our system is vast, it is the things we see in the night sky are our things. 3I Atlas challenged this comfort. When the initial trajectory was plotted, the numbers did not describe a closed loop. They described a hyperbolan open curve. In the language of orbital mechanics, this is defined by eccentricity. A perfect circle has an eccentricity of 0. A stretched ellipse, like that of a normal comet, has an eccentricity between 0 and 1. But Atlas had an eccentricity significantly greater than 1. The math was stark and unforgiving. This object was not orbiting the sun. It was not falling toward us. It was falling past us. It was a projectile fired from the dark, carrying enough speed to shatter the gravitational chains that bind every other object in our history. The scientific community, however, is built on a foundation of skepticism. Extraordinary claims require extraordinary evidence, and the claim that we were being visited by an object from another star system and interstellar interloper was profound. In those early days of detection, there was a collective hesitation to embrace the alien nature of Atlas. Astronomers looked for errors. They checked the calibration of the sensors. They scrutinized the atmospheric distortion data from the nights the images were taken. They ran the models again, and then again, hoping to find a mundane explanation. Perhaps, they reasoned, it was just a normal comet that had been kicked by Jupiter. We know that the gas giants act as gravitational bullies, altering the paths of smaller rocks that pass too close. A close encounter with Jupiter can slingshot a comet, adding speed and changing its direction. But when the timeline was reversed, tracing Atlas's path backward through the years, it showed no interaction with Jupiter. It hadn't gone near Saturn. It had sailed through the empty spaces between the planets, untouched and unbothered. Its speed was its own, not borrowed from a planetary encounter. Then came the hypothesis of outgassing. If a standard comet heats up as it approaches the sun, jets of gas can erupt from its surface. These jets act like thrusters, pushing the rock and artificially altering its speed, potentially mimicking a hyperbolic orbit. This was a safe, comfortable theory. It allowed us to keep Atlas within the family, classifying it as just a strange, active local comet. Telescopes were trained on it, searching for the telltale comet, the fuzzy halo of gas and dust that surrounds a waking comet. They looked for the tail that would confirm it was one of ours, melting in the solar warmth. But Atlas refused to perform. As it plunged deeper into the inner solar system, passing within the orbit of Mercury, it remained a stubborn, distinct point of light. There was no fuzzy halo. There were no jets. It was a dead stone, tumbling through the fire, seemingly immune to the heat. The absence of a tail was a silence that spoke volumes. It stripped away the last mundane explanation. Without jets to push it, the speed was purely gravitational, which meant the trajectory was real. The realization settled slowly, like dust in a quiet room. We were watching a physical piece of another solar system move through our own. For the first time in human history, we were not looking at light from the stars, but at matter from the stars. The sky was no longer a closed system. The invisible wall we had mentally erected around the sun had been breached. This was not a visitor returning home. It was a drifter passing through a town it didn't know, and we were the watchers at the window trying to comprehend the sheer scale of the journey it had already survived. The psychological shift was palpable within the observatories. The data on the screens ceased to be abstract numbers and became a narrative of isolation. If Atlas was truly interstellar, it had been traveling for a duration that defied human comprehension. It had likely been ejected from its birth system before our species existed, perhaps before the continents on Earth had settled into their current shapes. It had crossed the chasm between the stars, the light years of absolute nothingness, drifting in a vacuum so perfect and so cold that time itself seems to lose meaning. And now, purely by chance, it had stumbled into the warmth of our star. The odds of such an encounter were astronomical. The solar system is a tiny target in a vast, empty galaxy. For this rock to thread the needle, to pass within viewing distance of the third planet from the sun, was a statistical miracle. It forced us to confront a vertigo-inducing thought. If this one object happened to fly past us while we were watching, how many billions of others are flying through the dark, just out of range? How thick is the air of the galaxy with these silent stones? As the object neared its closest approach to the sun, its perihelion, the urgency of the observation grew. We knew our time was limited. Atlas was moving so fast that every hour changed the viewing geometry. It was not going to stay. It was not going to settle into an orbit and let us study it for decades. It was a transient event, a ghost passing through the room. The telescopes of the world, from the great dishes in the desert to the orbital eyes in the vacuum, swiveled in unison. The goal was no longer just to track it, but to read it, to analyze the light bouncing off its surface and decipher what it was made of, and perhaps where it had come from. The data that flowed back would paint a portrait of a world we could never visit, a place destroyed or disturbed eons ago, sending this lone messenger across the galactic void to tell us, simply, that we are not alone in the dark when we stand beneath the open sky on a clear, moonless night. We are victims of a beautiful and persistent illusion. We look upward and see a doom, a vast, curved ceiling scattered with points of light, to the human eye, and indeed to the primitive intuition that still governs our perception. The stars appear to be painted on a single surface, equidistant from us, like diamonds set into a velvet canopy. We perceive brightness, and we perceive color, but we do not perceive depth. The star Sirius appears brighter than the planet Saturn not because it is closer, but because it burns with a ferocity that masks the abyss between them. In this flattened version of the cosmos, a firefly blinking 10 feet away can momentarily outshine a galaxy burning 10 million light-years in the distance. We are trapped in a two-dimensional view of a three-dimensional universe, and breaking free of this flatness requires a leap of intellect that goes against the grain of our biology. This flattening effect does not disappear simply because we replace the human eye with a telescope. When a digital sensor captures an image of the night sky, it records a flat grid of pixels. A distinct point of light is merely a spike in data. Coordinate on an X and Y axis. There is no Z-axis in a photograph. There is no tag attached to the photon that tells us how long it has been traveling or how far it has come. Every image of space is a collapse of dimensions, compressing the near and the far into a single, misleading plane. To understand the true nature of an object like Atlas, or indeed any wanderer in the dark, astronomers must reconstruct the third dimension through deduction. They must build the depth of space out of time and geometry, creating a mental model that exists only in mathematics, for it can never be seen with the naked eye. The primary tool for breaking this illusion is parallax, a concept that is simple in principle but excruciatingly delicate in practice. It is the same phenomenon that occurs when you hold a finger up against a distant landscape and close one eye, then the other. Your finger seems to jump from left to right, while the mountains in the background remain still. In the cosmic theater, our planet is the shifting eye. As Earth orbits the sun, our vantage point changes by nearly 300 million kilometers every 6 months. We look at an object in January, and then again in July, and we measure the shift against the background of fixed stars, those distinct suns so incredibly distant that they effectively never move. However, for objects moving within our own solar system, or passing through it, the calculation is far more chaotic. We are not watching a static finger against a static mountain. We are watching a flying stone from a moving platform. The Earth is spinning at 1,000 miles an hour, and orbiting at 67,000 miles an hour. The object itself, be it a comet, an asteroid, or an interstellar vis-a-vis, also moving, tumbling along its own complex arc. We are two ships passing in the night, trying to gauge the distance between us, by the rate at which our lights cross. A rock that is small and close can mimic the motion of a rock that is massive and distant. A slow object near the Earth can trace the same path across the sky as a fast object near Mars. The data we receive is merely a streak, a scratch on the lens of the telescope. It is up to us to untangle the velocity from the distance, to separate the motion of the observer from the motion of the observed. This ambiguity creates a fertile ground for cognitive bias. For centuries, astronomy has been governed by a principle we might call solar system centrism. It is a natural, perhaps evolutionary, assumption that everything we see in our immediate vicinity belongs to us. We assume a shared history. If we spot a rock drifting past Jupiter, our default hypothesis is that the rock was born here, formed from the same primordial disk of dust and gas that built the Earth. We assume it is a cousin, a leftover brick from the construction of the planets. bound to the same central star. This bias is not born of ignorance, but of probability. The solar system is thick with debris. There are millions of asteroids in the main belt, and billions of comets in the outer reaches. Statistically, any random point of light we detect is overwhelmingly likely to be local. Therefore, the architecture of our tracking software and the intuition of our scientists are attuned to find ellipses. We look for closed loops because closed loops represent order, stability, and belonging. An ellipse implies that the object is a captive, that it will return, that it is part of the clockwork. When an object appears to deviate from this shape, it hints at a hyperbola, an open path with no return. The first instinct is not to rewrite our understanding of the cosmos, but to correct the error in our instruments. We assume we measured the parallax wrong. We assume the atmospheric turbulence shifted the pixels. We assume the object is just a standard comet behaving badly, perhaps pushed off course by a jet of gas. We couldn't seed out this hesitation to accept the alien as a protective mechanism. It keeps the maps clean. To admit that an object is hyperbolic is to admit that the solar system is not a fortress, but a sieve. It is to acknowledge that the space between the stars is not a sterile void, but a chaotic intersection of The illusion of proximity is a feeling that the night sky is a calm, static cover over the Earth's masks, a reality of terrifying kinetic energy. The galaxy is filled with shrapnel, ejected from dying star systems, wandering in the dark for eons. But because we cannot perceive the depth, because we cannot see the distance, we treat the sky as a unified whole. We group the intruder with the local residents, blinding ourselves to the profound difference between a rock that has orbited our sun for 4 billion years and a rock that has never seen our sun before today. The challenge of distinguishing the local from the foreign is compounded by the sheer clutter of our own backyard. We often visualize the solar system as a neat set of concentric rings: Mercury, Venus, Earth, Mars ending cleanly at Neptune. But this is a simplification. The solar system does not end. It fades. Beyond the planets, beyond the Kuiper belt, lies the Oort Cloud, a theoretical structure of immense proportion and mystery. It is a spherical shell of icy debris, the leftovers of the solar system's violent formation, pushed out to the very fringes of the sun's gravitational grasp. The Oort Cloud is not a thin ring. It is a fog that extends nearly halfway to the next star. It is the frontier where the sun's authority begins to waver, where gravity becomes a whisper. The objects out there move with agonizing slowness, drifting in the cold for thousands of years before completing a single circuit. Occasionally, one of these icy bodies is nudged perhaps by the gravity of a passing star, or the subtle tide of the galaxy itself, and it falls inward. It begins a long, accelerating dive toward the inner solar system, gathering speed as it falls, transforming from a lazy drifter into a high-velocity comet. When one of these long-period comets plunges into the planetary zone, it can look remarkably like an interstellar intruder. It comes from the dark. It comes from a steep angle. It moves with tremendous speed. To the observer on Earth, trying to calculate the orbit from a few nights of data, the difference between a rock falling from the edge of our own system and a rock falling from another star system is a matter of decimals. It is a difference of a few kilometers per second in speed, a fraction of a degree in the angle of arrival. We are trying to measure the curvature of a line that is almost straight. The difference between a very long, thin ellipse, which is local, and a hyperbola, which is alien, is the difference between a line that eventually closes and a line that stays open forever. In the short window of observation we have, those two lines look identical. Beneath the chaotic scattering of light that we call the night sky, there lies a second, invisible universe. It is a universe not of rock and fire, but of pure geometry. It is built from curves, arcs, and vectors, a silent, rigorous architecture that dictates where every atom is allowed to move. We tend to think of the solar system as a collection of objects, a star, 8 planets, and a swarm of debris. But to the physicist, the solar system is a collection of pathways. It is a vast web of tracks laid down by the warping of space-time, and for billions of years, the traffic on these tracks has followed a single, unbreakable rule. What resists must eventually fall. To understand the intruder, we must first understand the shape of captivity. In the language of celestial mechanics, captivity is a closed loop. It is a journey that, no matter how long or how difficult, eventually ends exactly where it began. The most perfect form of this captivity is the circle. The Earth, for instance, traces a path around the sun that is nearly a perfect circle, a geometry of absolute stability. Year after year, we ride this rail, keeping a constant distance from the fire, never leaving, never approaching, locked in a flawless, eternal waltz. But nature rarely deals in perfection. Most objects in our system do not travel in circles. They travel in ellipses. An ellipse is simply a circle that has been stretched, pulled by the competing forces of speed and gravity. Imagine a rubber band, perfectly round, then pinched at 2 points and pulled apart. It elongates. the center splits into two focal points, and the sun sits at one of them. This is the shape of the comet. A comet falling from the outer dark traces a long, thin ellipse. It dives inward, whipped around the sun by gravity, and then is flung back out into the cold. But even in its wildest, most distant exile, the comet is still tethered. It is slowing down as it climbs away, its kinetic energy draining into the potential energy of the climb until it reaches the apex of its flight. There, in the silence of the deep void, it stops, turns, and begins the long fall back. It is a prisoner on a long chain. Mathematicians measure the extent of this stretching with a single variable, eccentricity, denoted by the symbol $E. It is a number that quantifies the freedom of an orbit. A perfect circle has an eccentricity of 0, total symmetry, total submission to the center. As the orbit stretches, becoming an ellipse, the number climbs. It becomes 0.1, then 0.5, then 0.9. The comets from the Oort Cloud, those distant ghosts on the very fringe of the sun's influence, possess eccentricities of 0.99. They are stretched to the absolute limit, hanging by a thread, yet that thread holds. The number is still less than 1. The loop is still closed. They are still ours. Then, there is the threshold. The number 1 dot in the geometry of gravity. The number 1 represents a parabola. It is the razor's edge between staying and leaving. If an object possesses an eccentricity of exactly 1, it has precisely enough energy to escape the sun's gravity and never return, but with nothing to spare. It is a theoretical trajectory, a perfect balance where the object climbs away, slowing down forever, approaching a standstill at the end of time, but never quite turning back. It is the geometry of the escape artist who clears the wall by the width of a single atom. But when the data from the object designated 3I Atlas began to resolve, the numbers did not show a circle. They did not show an ellipse. They did not even show a parabola. They revealed a shape that had never been catalogued in the history of our solar system's distinct architecture. The eccentricity was approximately 1.2. This was not a decimal error. This was a hyperbola. A hyperbola is the shape of the outsider. Unlike the ellipse, which curves back upon itself to form a ring, the hyperbola is an open curve. It comes from the infinite distance, bends once around the source of gravity, and then shoots back out toward the infinite distance in a different direction. It is a line that never heals. It implies that the object is not borrowing energy from the sun to make its journey. It brought its own means that the object was never moving slowly enough to be captured. It hit the solar system with such ferocity that the sun's gravity could only deflect it, not claim it. That to visualize what this number 1.2 truly means, we must change our perspective of the solar system. We must stop seeing it as a flat plane of planets and instead see it as a gravity well. Imagine the sun as a heavy weight sitting in the center of a stretched fabric, creating a deep, funnel-shaped depression. The planets are like marbles rolling around the inner walls of this funnel. They have speed, which keeps them from falling into the hole, but they do not have enough speed to climb up the slope and roll out onto the flat table beyond. They are trapped in the well, trading height for speed, forever circling the drain. A comet from the Oort Cloud is a marble dropped from the very rim of the funnel. It rolls down the steep slope, gaining immense speed as it nears the bottom though. So Nan then uses that speed to shoot back up the other side. But because it started at the rim, it only has enough energy to reach the rim again. It rises, slows, and just as it kisses the edge of the well, gravity pulls it back down. It cannot escape the pit because it was born in the pit. It is bound by the law of conservation of energy. You cannot get out more than you put in. Atlas was different. Atlas did not start at the rim. It arrived from the flat table beyond, already moving. It drove over the edge of our gravity well with an initial velocity that was not 0. As it fell into the funnel, it gained all the speed that a normal comet gains from falling, but it added that speed to the velocity it already possessed. It was a marble thrown into the pit, not dropped. When it swung around the sun and began its climb back out, it didn't slow to a halt at the rim. It still had that extra reserve of energy, that hyperbolic excess. It crested the wall of our solar system without hesitating, carrying its momentum back out into the galaxy. The discovery of this hyperbolic trajectory was a quiet thunderclap in the halls of astronomy. It shattered the assumption of isolation, more effectively than any photograph could. A photograph shows us a surface. A trajectory shows us a history. The geometry of the ellipse tells the story of a family, of objects born from the same dust, bound by the same laws, returning to the same heart. The geometry of the hyperbola tells the story of a stranger. It speaks of an origin far beyond the reach of our sun's heat, a journey that began in the unknown and will end in the unknown. When we looked at the curve of Atlas's path, we were looking at a line drawn by an alien hand. It was a visiting card from the void. The mathematics were crisp and indifferent. There was no ambiguity in the eccentricity. The object was not falling, it was driving. And as we traced that open curve, backward, extrapolating the line out of the well and into the dark, we began to realize just how fast it had been moving before it ever saw our sun. This was not a drifter caught in a current. This was a bullet. If geometry is the map of the heavens, then light is the ink in which the history of worlds is written. The trajectory of the object designated 3I Atlas told us where it was going, and where it had been, revealing the stark hypervelocity curve of a traveler that had broken free from the gravity of its home star. But the curve of a path, no matter how precise, is silent on the nature of the traveler itself. It tells us the mass and the speed, but it does not speak of the substance. To know what the object was made of, to touch the dust of a foreign solar system, without ever leaving the surface of our own we had to stop looking at the motion and start looking at the reflection. We had to catch the light. This is a task of immense delicacy. In the vast, airless amphitheater of space, the only connection we have to physical reality is the stream of photons that wash over the Earth. Every star, every planet, and every drifting rock is constantly broadcasting a signal, a continuous stream of information encoded in the electromagnetic spectrum. When sunlight hits an object, the surface absorbs certain wavelengths and repels others. The light that bounces back is not the same as the light that arrived. It has been altered. It carries a signature. It has been stamped by the chemical bonds of the material it touched. By capturing this reflected light and passing it through the prism of a spectrometer, the astronomers can fan it out into a rainbow, revealing the gaps, the dark, missing lines where the colors should be. These gaps are the fingerprints of the elements. They tell us, with absolute certainty, whether we are looking at iron or ice, carbon or silicate, the familiar or the unknown. But Atlas was not a cooperative subject. It was not a bright, burning star broadcasting its identity to the universe. It was a shard of rock, small and incredibly dark, tumbling through the void. It produced no light of its own. It merely borrowed the illumination of our sun, and because it was so small, perhaps the size of a city block, and so distant, the amount of light it reflected was infinitesimally small. It was like trying to analyze the chemical composition of a piece of coal falling through the night sky 1,000 miles away, lit only by the beam of a distant flashlight. The observatories that turned their gaze toward Atlas were not just taking pictures, they were deploying light buckets, giant concave mirrors designed to harvest these scarce photons from the sky. The urgency was palpable. The object was already receding, fading by a magnitude every few days. The stream of data was drying up. Every cloud that passed over a telescope in Hawaii or Chile, every tremor of atmospheric turbulence, meant the permanent loss of information that had traveled millions of years to reach us. The astronomers were engaged in a frantic archaeological dig, where the artifact was dissolving before their eyes. The first results to come back were not detailed chemical breakdowns, but broad strokes of color. In the visible spectrum, Atlas was red, but this was not the vibrant, rusted red of Mars, nor the bright, fiery red of a dying star. It was a deep, dull, spectral red, a color that speaks of age and exposure. In the context of the outer solar system, this specific hue is a sign of suffering. It is the color of organic chemistry that has been tortured by radiation. We call these compounds tholins. They do not exist naturally on Earth. Our thick atmosphere protects us from the harsh energies that create them. But in the vacuum of space, organic molecules like methane and ethane are subjected to a relentless bombardment of cosmic rays energy particles, ejected from supernova and galactic cores. Over eons, this radiation breaks the chemical bonds of the ice, rearranging the atoms into complex, chaotic chains of heavy hydrocarbons. The ice turns to sludge, and the sludge turns to a hard, reddish crust. It is a callus, a layer of scar tissue that builds up on the skin of an object that has spent too long in the open void. The presence of this deep red crust on Atlas was the first physical confirmation of its journey. It told us that this object had not been hiding in the protective warmth of a star system. It had been drifting in the interstellar medium, exposed to the raw, unfiltered radiation of the galaxy for a very long time. The redness was a clock. It suggested that Atlas had been tumbling in the dark for millions, perhaps billions, of years, allowing the cosmic rays to slowly bake its surface into this distinct, asphalt-like substance. It was wearing the tan of the deep universe. However, as the spectral data became more granular, a strange and unsettling sense of familiarity began to creep into the analysis. We expected the alien. The narrative of an interstellar visitor primes the imagination for the exotic materials we have never seen, isotopic ratios that defy our periodic table, or a surface composition that screams of a genesis in a completely different stellar nursery. We wanted a rock made of diamond, or a shard of pure metal, or a structure so bizarre that it would force us to rewrite the textbooks on planetary formation. Instead, the spectrum of Atlas looked confusingly like the spectrum of the objects we find in our own backyard. Specifically, resembled the D-type asteroids that inhabit the outer rim of the asteroid belt and the Trojan clusters of Jupiter. These are some of the oldest, most primitive objects in our solar system, dark and reddish, rich in carbon and volatiles. If you were to take a piece of the primitive solar nebula, the dust cloud from which the Earth was born, and freeze it, then bake it in radiation, for 4 billion years, it would look like a D-type asteroid, and it would look like Atlas. This similarity created a paradox that was far more troubling than a completely alien signature would have been. If Atlas came from another star, why did it look so much like the rubble left over from our own sun? The galaxy is a vast and varied place. Stars have different metallicities. They burn at different temperatures and condense out of clouds with different chemical mixtures. We expected a visitor from the Pleiades, or the Hyades, to carry the distinct chemical flavor of its home. But Atlas was mute on its origins. It wore the generic uniform of the cosmos. This forced scientists to confront a profound question about the universality of chemistry. Perhaps the recipe for building a solar system is the same everywhere. Perhaps the disk of dust and gas that swirled around our infant sun was not unique, but merely a standard template repeated trillions of times across the spiral arms of the Milky Way. If Atlas was indistinguishable from a Jupiter Trojan, it implied that the stuff of worlds is common currency. It suggested that if we were to travel to the star system from which Atlas was ejected, we might find planets that look hauntingly like our own, built from the same silicate bricks, covered in the same organic dust, subject to the same laws of weathering and time. The disappointment of the familiar was, in fact, a deeper revelation. It bridged the gap between the local and the universal. We often think of us and them, our solar system, versus the alien void. But the spectrum of Atlas suggested that the void is filled with debris that is essentially kin to us. The distinction is not in the material, but in the location. It was a realization that stripped away some of the romance of the alien, replacing it with a quiet, terrifying solidarity. The universe is made of the same ash, no matter which fire it fell from. Yet, the spectral was not entirely silent. Beneath the dominant red slope of the tholins, there were subtle absorption features, teeny dips in the graph that hinted at something more volatile. As the object tumbled, presenting different faces to the sun and to our telescopes, the signal fluctuated. We were seeing an average of the surface, a blur of the whole rotating body. But was the redness uniform? Was it a solid block of this cosmic asphalt? Or was the red merely a thin rind covering something else? We know from our own comets that the dark crust is often a disguise. The comet 67P, visited by the Rosetta spacecraft, was black as coal on the outside, but when the surface cracked, it revealed brilliant, white ice beneath. The tholins are the skin, but the ice is the blood. The question that haunted the spectral analysis was whether Atlas had a heart of ice. If it did, why wasn't it melting? It was passing within the orbit of Mercury, subjected to a solar intensity that boils lead. A standard comet would be screaming with escaping gas. It would be surrounded by a cloud of water vapor, carbon monoxide, and cyanide. The spectrum would be lit up with the emission lines of these gases, glowing like neon signs. But Atlas was dry. The spectrum showed no strong emission lines. There was no bright spike of hydrogen, no glowing fingerprint of oxygen. The silence of the gas was contradictory to the color of the surface. If it was a D-type asteroid rich in volatiles rich in ice, the heat should be destroying it. It should be cracking open. The fact that it wasn't suggested that either it was a rock depleted of all its ice eons ago, or the crust was so thick, so insulated, and so baked by its interstellar journey that it had become a sealed sarcophagus, trapping the ancient ices deep within its core, refusing to let them go even in the face of the sun. We were looking at a sealed bottle from another time and place. The label on the outside, the red tholins, told us it had traveled a long way, but the contents remained hidden. We were scratching at the surface with our eyes, trying to peel back the layers of radiation damage to see the pristine material underneath. And as the days ticked by, and the object grew dimmer, the data became noisier. The clean lines of the spectrum began to fray into static. We were losing the signal. We had the color, and we had the chemistry of the skin, but the soul of the object, a bulk composition that would confirm its identity, remained just out of reach, hidden behind the glare of the sun and the vastness of the retreating dark. For the first few months of the observation, the narrative of Atlas was defined by its randomness. The initial trajectory calculations, drawn in the haste of the discovery, pointed the object's origin toward the solar apex, the direction in the constellation Lyra toward which our own sun is constantly moving. This was a comfortable, statistically probable answer. It suggested that Atlas was simply roadkill on the galactic highway. Just as a car moving down a freeway is most likely to strike insects hovering directly in its path, our solar system, sweeping through the Milky Way at 220 kilometers per second, had simply scooped up a piece of debris that was floating in front of us. This theory reinforced the idea of the object as a drifter, a piece of cosmic flotsam without a specific history, waiting in the dark to be hit by the windshield of our star's gravity. But gravity is a strict accountant. It demands that the motion of every object balance perfectly against the mass of the bodies it passes. As Atlas swung around the sun and began its retreat, Astronomers continued to measure its position with the obsession of cartographers mapping a new coastline. They used astrometry, the precise measurement of light on a grid, to predict where Atlas would be tomorrow, next week, and next month. If the object were a dead stone, governed solely by the laws of Isaac Newton, these predictions should have been flawless. The rock should have been exactly where the gravity of the sun and the planets dictated it to be, down to the millimeter. It wasn't. The divergence began as a whisper in the datasets. At first it was dismissible, a matter of a few hundred kilometers, in a journey of millions. But as the weeks passed, the gap between the predicted path and the actual path widened. Atlas was arriving at its checkpoints early, was moving faster than gravity alone could explain. It was as if something was pushing it from behind, a gentle but persistent hand shoving it away from the sun. In the rigid equations of orbital mechanics, this is known as non-gravitational acceleration, a dry term that masks a profound implication. The object is not just falling. It is flying. This acceleration forced a revisit of the spectral silence discussed in the previous chapter. We had seen no tail, no coma, no bright jets of gas. We had assumed Atlas was a dead rock, but the motion told a different story. The only way for an object to accelerate in a vacuum without an engine is through the sublimation of ice. When sunlight hits a frozen surface, the ice turns to gas and expands violently, shooting out into the void. For every action, there is an equal and opposite reaction. A jet of gas shooting north pushes the rock south. This is the rocket effect. The paradox was that we couldn't see the rocket. The gas-driving Atlas was stealthy. It was likely composed of water vapor or perhaps pure molecular hydrogen, gases that are transparent to the optical cameras that were watching it. Or perhaps the dust it ejected was made of large, heavy grains that didn't scatter light in the way fine dust does. Whatever the mechanism, the conclusion was inescapable. Atlas was alive. It was outgassing. And this invisible thrust, however weak, was altering its course every second. This realization shattered the initial map of its history. To find out where an object came from, scientists perform a process called backward integration. They take the current position and velocity of the object, reverse the arrow of time, and run the simulation in reverse. They unwind the orbit, backing it out of the solar system, across the void, and into the deep past. But a simulation is only as good as its inputs. The first models had assumed gravity was the only force at play. They had traced a line based on a passive fall. Now, they had to trace a line based on a powered flight. They had to account for the thrust. If Atlas was accelerating away from the sun now, it meant it had been decelerating on its way in. It meant the drag and the push of its own gases had been subtle architects of its path for years, perhaps decades. When the mathematicians added this variable, the non-gravitational force, to the backward integration, the thread of the trajectory did not land in the same place. The line on the star map began to drift. It detached itself from the solar apex, that generic front windshield of the sky, and swung across the celestial sphere. It moved away from the assumption of randomness. The aerobars, which had previously covered a swath of sky large enough to contain thousands of potential source stars, began to tighten. The new calculation stripped away the noise. It was no longer looking for a needle in a haystack. It was following a compass needle that had suddenly found north. It was a realization that stripped away some of the romance of the alien, replacing it with a quiet, terrifying solidarity. The universe is made of the same ash, no matter which fire it fell from, yet the spectrum was not entirely silent. Beneath the dominant red slope of the tholins, there were subtle absorption features, tiny dips in the graph that hinted at something more volatile. As the object tumbled, presenting different faces to the sun and to our telescopes, the signal fluctuated. We were seeing an average of the surface, a blur of the whole rotating body. But was the redness uniform? Was it a solid block of this cosmic asphalt? Or was the red merely a thin rind covering something else? We know from our own comets that the dark crust is often a disguise. The comet 67P, visited by the Rosetta spacecraft, was black as coal on the outside, but when the surface cracked it revealed brilliant, white ice beneath. The tholins are the skin, but the ice is the blood. The question that haunted the spectral analysis was whether Atlas had a heart of ice. If it did, why wasn't it melting? It was passing within the orbit of Mercury, subjected to a solar intensity that boils lead. A standard comet would be screaming with escaping gas. It would be surrounded by a cloud of water vapor, carbon monoxide, and cyanide. The spectrum would be lit up with the emission lines of these gases, glowing like neon signs. The Atlas was dry. The spectrum showed no strong emission lines. There was no bright spike of hydrogen, no glowing fingerprint of oxygen. The silence of the gas was contradictory to the color of the surface. If it was a D-type asteroid rich in volatiles, rich in ice, the heat should be destroying it. It should be cracking open. The fact that it wasn't suggested that either it was a rock depleted of all its ice eons ago, or the crust was so thick, so insulated, and so baked by its interstellar journey that it had become a sealed sarcophagus, trapping the ancient Essos deep within its core, refusing to let them go even in the face of the sun. The orbit of 3I Atlas was not merely a path through space. It was a descent into a furnace. For millions of years, the object had known only the absolute zero of the interstellar void, a temperature so low that the very motion of atoms slows to a crawl. In that deep freeze, chemistry is paused. The Essos that bind a world together, carbon monoxide, nitrogen are, as hard as granite, forming a bedrock that can survive the gentle erosion of cosmic dust. But as Atlas fell toward the sun, crossing the invisible borders of our planetary system, the environment shifted with violent rapidity. It was plunging into a regime of energy it was never designed to withstand. The point of closest approach, known as perihelion, is the ultimate stress test for any celestial body. It is the moment where the abstract curves of orbital mechanics collide with the brutal reality of thermodynamics. As Atlas swept past the orbit of Mercury, the sun ceased to be a distant star and became an overwhelming physical presence, a wall of plasma dominating the sky. At this range, the solar radiation is not just light, it is a physical hammer. It strikes the surface of the rotating object with an intensity that can melt lead, stripping away the outer layers and driving a wave of heat deep into the frozen heart of the stone. In the vacuum of space, the reaction of ice to this sudden assault is immediate and catastrophic. On Earth, ice melts into water, a gentle transition from solid to liquid. But in the void, where there is no atmospheric pressure to hold a liquid state, the phase of water is skipped entirely. This is the process of sublimation. The solid ice does not melt, it explodes. It transitions instantly from a frozen crystal into a rapidly expanding gas, occupying thousands of times the volume it held a microsecond before. This phase change is the engine of cometary activity. It is what turns a dirty snowball into a spectacle. As the heat penetrates the dark crust, it reaches the pockets of ice trapped beneath. The ice sublimates, turning into a hypersure gas that is trapped within the rock. The pressure builds until the crust can no longer contain it, and the surface ruptures. Jets of gas and dust erupt outward, creating the tails and comas that we admire from Earth. But this process is governed by a strict hierarchy, a chemical ladder known as the volatile threshold. Not all ices are created equal. They each have a specific breaking point, a temperature at which they surrender their solidity. At the bottom of the ladder are the hypervolatiles, nitrogen and carbon monoxide. These substances are so unstable that they can sublimate even in the cold darkness of the outer solar system, driven by the faint warmth of a distant sun. If an object is rich in these ices, it will begin to sizzle and outgas while it is still, as far out as Neptune. These are the active at a distance comets, the ones that announce their arrival early. Above them sits carbon dioxide, a slightly more stubborn ice that requires the warmth of the asteroid belt to wake up. And at the top of the common volatiles is water. Water ice is the bedrock of the comet. It is tough and resilient, requires the intense heat of the inner solar system, roughly the distance of the Earth from the sun, to begin in earnest. This thermal layering creates a predictable sequence of events for any object falling toward the sun. It should peel like an onion. First, the nitrogen boils off, then the carbon monoxide, then the carbon dioxide, and finally, as it screams past the sun, the water ice vaporizes, creating the massive hydrogen envelopes that define the great comets of history. Atlas, however, presented a thermal puzzle. Based on its trajectory from the deep interstellar cold, it should have been preserved in a pristine state. It should have been a reservoir of those hypervolatiles, the nitrogen and carbon monoxide that boil at the slightest touch of heat. As it crossed the frost line, the boundary where water ice turns to gas, we expected a coronation. We anticipated that the accumulated heat of the approach would trigger a cascade of sublimation, turning the object into a blazing torch of escaping gas. But the torch did not light. Or rather, it lit with a strange, suffocated flicker. The observation data during perihelion showed that while Atlas was accelerating, proving that some gas was escaping, it was not shedding mass in the quantities that a standard model would predict. The object was absorbing a colossal amount of solar energy, soaking up the heat like a dark sponge, yet the surface remained largely intact. It was not shedding its skin. This resilience forces us to consider the structural engineering of the object itself. In our solar system, comets are often described as rubble piles. They are loose aggregations of dust and gravel held together by the weak gravity of their own mass and the glue of their ices. They are fragile. When a rubble pile gets too close to the sun, the thermal stress usually shatters it. The heat causes the rock to expand, cracking the icy glue, and the comet disintegrates into a stream of gravel. This is the death of a comet, a common fate for Sun-Grazers. Atlas passed significantly closer to the sun than many comets that have disintegrated, yet it survived the point of maximum heat. It emerged from the perihelion passage largely whole, though altered. This implies that the internal structure of Atlas was not a loose rubble pile. It suggests a tensile strength that is higher than the comets we are used to. Perhaps the material was not just glued together by ice, but by some other process. Or perhaps the glue itself was different. We must hypothesize about the nature of an alien matrix. In the stellar nursery where Atlas was born, the chaotic moving group, I identified in our backward integration the conditions for formation may have favored a different kind of architecture. If the object was formed in a region rich in organic compounds, the cement holding the dust grains together might be a tar-like substance rather than a brittle ice. A matrix of heavy hydrocarbons would be more resistant to thermal shock. It would not shatter like glass. It would soften like asphalt. As the heat wave traveled from the surface to the core, it would have encountered this alien geology instead of the sharp, explosive sublimation of pure ice pockets. The volatiles within Atlas may have had to fight their way through a dense, porous labyrinth of this organic tar. The gas would be generated, yes, but it would be trapped in a complex network of micropores, leaking out slowly rather than bursting forth. This would explain the fizzle, the lack of a bright coma. The object was outgassing, but it was suffocating its own emissions. The tension within the object during this phase would have been immense. We can imagine the interior of Atlas as a pressure vessel. The core is still frozen, remembering the cold of the void, while the crust is baking at hundreds of degrees. The differential expansion creates deep, groaning fractures in the body of the rock. The silence of space would be broken by the sound of the object tearing itself apart from the inside. The dull thud of shifting strata as the shape of the world warped under the thermal load. This was the trial of the volatile threshold. It was not just a measure of temperature, it was a measure of history. The way an object breaks tells you how it was built. A house of cards collapses differently than a house of brick. Atlas was trembling, vibrating with the internal energy of trapped gas, skating on the edge of total disintegration. It was a battle between the gravity holding it together and the vapor pressure trying to blow it apart. And as it rounded the sun, heading back out toward the safety of the dart, the question was not whether it had survived, but what it had lost in the fire. The fizzle was not a failure of the object to perform. It was a clue. It whispered that the ingredients of this world were mixed in a different bowl, baked at a different temperature, and bound by a chemistry that resisted the simple, violent rules of our local star. There's a profound comfort in the idea of the island. For most of human history, we have viewed our solar system as exactly that, a solitary outpost of warmth and order, surrounded by an ocean of nothingness so vast that it acts as a quarantine. We believe that the void between the stars was an absolute barrier, a dark silence that ensured that what happened in the Centauri system stayed in the Centauri system, and what happened here belonged solely to us. The stars were lights to be admired, not neighbors to be visited, and certainly not neighbors who threw stones into our backyard. This perception of isolation was built on the scale of the distances involved, the light years that seem insurmountable to our biological minds. But the trajectory of the object, designated 3I Atlas, has dismantled this comfort. It has forced us to abandon the map of the island and adopt the map of the archipelago. We now understand that the galaxy is not a collection of sealed rooms. It is a single, vast, circulating ecosystem. It is a fluid medium where gravity acts as the current and matter is the cargo. The error we made in the early days of the discovery, assumption that Atlas was a random statistical fluke, was born from a failure to appreciate the sheer density of the traffic on the galactic highway. We treated the visitor as an anomaly, a 1 in a billion event, when in reality, it was merely the first raindrop we happened to catch in our hands during a storm that has been raging for eons. To grasp the reality of this exchange, we must look at the galaxy not as a static painting, but as a metabolic system. Stars are born in clusters, violent and chaotic nurseries where gravity swings wildly, ejecting trillions of tons of rock and ice into the deep cold. Solar systems do not form neatly. They are messy, inefficient construction sites. In the process of building planets, a star system shreds and discards a significant percentage of its building materials. These discarded bricks, the astrons, the cometesimals, are flung outward, escaping the gravity of their parent stars to become free-floating wanderers. They enter the interstellar medium, adding to a background population of debris that permeates the entire Milky Way. This constant shedding creates a cosmic background noise that is physical, not auditory. The space between the stars is filled with a blizzard of these frozen stones. They are the shrapnel of creation, drifting through the vacuum, waiting to be captured or deflected by the next gravity well they encounter. When we run the numbers, extrapolating from the detection of Atlas and its cometary cousin Borisov, the results are staggering. Statistical models suggest that at any given moment, there is at least one interstellar object of significant size inside the orbit of the Earth. Within the orbit of Neptune, there are likely thousands. We are not sailing through empty space. We are sailing through a fog of other people's history. The only reason we haven't seen them before is that they are dark. They are small, and until very recently, we we were effectively blind. This realization brings us to the concept of lithopanspermia. It is a formidable word, often hijacked by science fiction to tell stories of alien invasions or spores drifting through space to colonize new worlds. But in the sober light of planetary science, it refers to a mechanism much more fundamental and much more common. It simply means stone transfer. It is the proposition that rocks are the couriers of the galaxy. If a planet is struck by a massive espanyol, the impact can launch debris into space with enough velocity to escape the star system entirely. These rocks, liberated from their home, drift across the light years, carrying within them the chemical signature of the world they left behind. We must strip the sensationalism from this idea and look at the physics. Atlas was likely not a carrier of life. Its exposure to cosmic rays had sterilized its surface eons ago. It was a carrier of ingredients. It was a package of distinct chemistry delivered to our doorstep. If we view the galaxy as a kitchen, then these interstellar objects are the way the ingredients are mixed. A star system forms, cooks its elements into complex molecules, and then, through gravitational ejection, shares a spoonful of that mixture with the rest of the galaxy. The periodic table is universal. Carbon is carbon, whether it is in the spiral arm of Andromeda or the coal mines of Pennsylvania. But the recipes, the specific molecular arrangements, the isotopic ratios, the distinct flavors of organic chemistry vary from star to star. The existence of Atlas proves that this cross-contamination is not theoretical. It is inevitable. Over the 4 billion-year history of our solar system, we have undoubtedly been bombarded by millions of these visitors. Most pass through without touching us, ghosts in the night, but some strike, some burn up in our atmosphere, sprinkling their alien dust into the air we breathe. Others crash into the moon or Mars, burying their secrets in the regolith. And occasionally, one might strike the early Earth, delivering a payload of water, or organics that was brewed in the light of a different sun. This perspective shifts our understanding of our own origins. We tend to think of the Earth as a closed system, a biology that arose from a local soup. But if the galaxy is a blizzard of exchanging rocks, then no system is truly closed. The water in our oceans, the carbon in our DNA, the nitrogen in our atmosphere, while mostly local, they have been seasoned by a dusting of material from across the Milky Way. We are a collage. In a mistake of thinking Atlas was a random wanderer obscured this grand connectivity? By tracing it back to the or Columba associations, we realize that specific regions of the galaxy are actively exporting their material to us. We are downstream from their creation. The probability of detection is the final piece of this puzzle. To see Atlas was to win a lottery against the dark. The object was small, dim, and fast. The fact that our telescopes happened to be pointing at the right patch of sky at the right moment, and that our algorithms were sensitive enough to pick out its motion. It implies that the population of these objects must be immense. You do not find a 4-leaf clover by walking across a football field unless the field is full of clover. The detection implies the density. It tells us that for every Atlas we catalog, there are trillions that pass unseen, a silent river of stones flowing through the solar system, weaving the history of the galaxy into a single, complex tapestry. We are living in a busy intersection. The silence of the night sky is an illusion of our limited vision. In reality, the traffic is heavy, and it flows in all directions. The boundaries we draw around our solar system, the heliopause, the Oort Cloud, are magnetic and gravitational borders, not physical walls. They are porous. The galaxy breathes. It inhales the debris of dying stars and exhales the shrapnel of new ones. Atlas was a single breath, caught in the light, revealing the atmosphere of the universe to be thick with the potential of matter on the move. The departure of a ghost is always less dramatic than its arrival. There was no specific moment when the object designated 3I Atlas officially left us. There was only a slow, agonizing fade into the static. As it crossed the orbit of Mars, heading outward, it was still a distinct, trackable point of light, a tangible anomaly on the screens of the Deep Space Network. But as it pierced the orbit of Jupiter, the distance began to swallow it. The signal-to-noise ratio, which had been the heartbeat of the investigation for months, began to falter. The distinct curve of the hyperbola dissolved into a cloud of probability. The sharp spectral lines that had hinted at its alien chemistry blurred into the background radiation of the galaxy. Eventually, the most powerful eyes we possessed, the space telescopes hanging in the silence above our atmosphere, took their final frames. They did not capture a farewell wave or a sudden burst of speed. They captured a smear, a faint, dying pixel struggling against the black. And then, on a Tuesday that felt like any other, the computers simply could not find it. The coordinates were checked, the exposure times were lengthened, but the dark had reclaimed its own. Atlas had slipped back into the anonymous, freezing void from which it came, returning to the profound silence that is its natural state. It was gone, continuing its fall toward a destination that likely does not yet exist, leaving us standing at the window, pressing our hands against the glass, realizing for the first time that the glass is not there. The silence that followed was different from the silence that preceded it. Before Atlas, the emptiness between the stars was perceived as a barrier of vast, sterile moat that protected our solar system from the chaos of the galaxy. We believed that we lived in a fortress, a clockwork mechanism of planets and moons that functioned in isolation. But the departure of the visitor left behind a permanent fracture in that perception. We can no longer look at the night sky and see it as a painted ceiling. We now know it as a highway. The void is not empty. It is full of traffic. It is a circulating current of matter, a river of stones and dust that flows through the spiral arms. And for a brief, terrifying moment, we dipped our fingers into the water and felt the chill of the current. This shift in perspective is the true legacy of the encounter. It is not the data on the hard drives, nor the papers published in journals, but the fundamental change in our sense of place. We are not an island. We are a sieve. The solar system is a permeable structure, constantly inhaling and exhaling the substance of the universe. The gravity of the sun is a powerful anchor, yes, but it is not an absolute wall. The border is open. The realization brings with it a sense of vertigo, a sudden awareness of the drafts blowing through the room we thought was sealed. As we watched Atlas recede, the narrative flipped. We stopped asking what the object meant for us, and started asking what we mean for the galaxy. If a rock from the Carina Association can travel 40 million years to skip like a stone across our atmosphere, then the reverse must also be true. Our sun is not just a passive receiver of debris. It is an active participant in the galactic exchange. For 4.5 billion years, since the violent tantrums of its youth, our star has been ejecting its own children into the dark. Every time a comet from the Oort Cloud is nudged by a passing star or the galactic tide, it falls inward. Some are captured, but many are flung out. They swing around Jupiter, steal a fraction of the giant planet's momentum, and are slingshotted into the interstellar medium. They become hyperbulous. They become the intruders. At this very moment, there are billions of object shards of Earth's sibling planets, frozen chunks of our primordial nebula drifting through the void between the stars. They are the atlas of someone else's sky. They are the dark, silent ambassadors of the solar system, tumbling and over in, carrying the chemical signature of our home to worlds we will never see. This reciprocity transforms the fear of the alien into a recognition of kinship. We are not the victims of a cosmic bombardment. We are participants in a cycle. The galaxy is a vast, slow-motion mixing bowl. The material that makes up the planets, the asteroids, and even the living things on Earth is not static. It is borrowed. The atoms in our bodies were forged in the hearts of dying stars, blown across the galaxy, condensed into a nebula, formed into a planet, and perhaps, one day, will be ejected again to seed a cloud on the other side of the Milky Way. Dust to dust is not just a statement of mortality. It is a statement of orbital mechanics. The departure of Atlas forces us to confront the scale of time. The journey of this single rock bridges eras that the human mind struggles to encompass. When it left its home, mammals were just beginning to conquer the Earth. As it crossed the Gulf, civilizations rose and fell. Continents drifted, and ice ages came and went. And now that it has left us, it will travel for eons more before it encounters another star. It is a time capsule that will likely outlive the species that briefly named it. There is a melancholy in this, a reminder of the brevity of our watch. We are the blink of an eye. The rock is the long, unblinking stare. Yet, within that melancholy, there is a strange hope. We are small, and we are brief, but we are also the only part of the universe that has learned to see itself. The rock does not know it is traveling. It does not know it has visited a yellow dwarf star in the Orion Spur. It is dead matter, obedient to the laws of motion. We are the witnesses. We are the ones who can stand on a small, wet rock and deduce the history of a stone that passed us at 90 kilometers per second. We can reconstruct its birth, its exile, and its composition without ever touching it. This capacity for understanding, for reaching out with our minds, where our bodies cannot go is, our defiance against the scale of the dark dot. As the data streams dried up, the astronomers returned to their other work. The telescopes slewed to new targets, distant galaxies, exploding stars, the hunt for exoplanets. The excitement of the chase faded, replaced by the quiet routine of the long watch. But the sky had changed. It looked the same constellations, the same familiar planets, but the feeling was different. The backdrop had acquired depth. We now knew that the darkness was not a void, but a plenum, thick with the history of other worlds. We began to calculate the odds of the next arrival. The model suggested that if we looked hard enough, if we built telescopes with wider fields of view and faster processing speeds, we would see them everywhere. We would realize that we are standing in a blizzard. Atlas was simply the first snowflake we managed to catch on our tongue. The realization is humbling. We are not the center of the drama. We are just a location, a coordinate, a way station on a journey that has no final destination. The fading of Atlas also marked the end of our ownership. While it was here, within the sphere of our sensors, we named it, We classified it, we projected our theories and our anxieties onto it. We called it a scout, a ship, a fragment, a mistake. We made it ours. But as it crossed the heliopause, the boundary where the solar wind gives way to the interstellar gale, it stripped itself of our labels. It ceased to be 3I Atlas. It became once again simply a piece of the universe, nameless and indifferent. It does not care that we studied it. It does not care that we exist. It simply moves. And in that movement, there is a lesson for the stationary. We cling to our planet, to our borders, to our specific moment in time. We build walls and define ourselves by what is inside them. But the universe recognizes no such distinctions. Gravity does not respect national borders or the heliosphere. It tugs at everything equally. The carbon in the tholins on Atlas's surface is the same carbon that bonds the sugar in our coffee. The water ice trapped in its core is the same water that freezes in our poles. The distinction between here and there is a construct of our limited reach.